Thank you, Karina and Clara, for accepting our invitations. It takes some work to prepare the slides and address our questions. We'll start the seminar today with Karina. Karina von Schuckmann is a physical oceanographer specialized in ocean climate monitoring, working at Mercator Ocean in France. Her interest lies in understanding the role of the ocean in the Earth's climate system. She is working on the Earth's energy imbalance and the Earth's heat inventory, particularly concerned on the role of the ocean warming under climate change. She is, among others, the lead of the Copernicus Marine Services Ocean Reporting Framework, a lead author of reports for IPCC and IOC, member of the European Academy of Sciences, and multiple international science panels. Thank you, Karina, for joining us today, and it's all yours.
Thank you very much, Sergey, for the introduction, and I would like to thank the Science Committee for the invitation to this seminar today. So I have been tasked to provide insights on a general title, which is Heat in the Ocean. According to my core expertise, I have decided to orientate this talk in terms of global distribution of heat in the ocean, albeit recognizing that there are large amounts of work, in particular from the Reanalysis community, on regional heat redistribution. So I will start with a very straightforward and clear message in terms of for the introduction. And this is that due to the emissions of heat-trapping gases resulting from human activities, the global ocean has warmed, as it has taken up more than 90% of the excess heat in the climate system, making climate change irreversible. So the ocean will continue to warm throughout the 21st century. By 2100, the ocean will take up 2 to 4 times more heat if global warming is limited to 2 degrees and up to 5 to 7 times at higher emission scenarios. So these are messages which have been provided by the special report on IPCC and the latest R6 report published last year. So what is the specific role of and the link of ocean warming in terms of the Earth's heat inventory? So due to the emission of greenhouse gases, there's an current imbalance at the top of the energy between incoming and outgoing radiation. And due to this, there is an accumulation of heat in the Earth system, and 90% of this heat is stored in the ocean. And the rest, the next dominant term is the land, then the cryosphere and atmosphere is available to warm the land, to melt the ice in the cryosphere, and to warm the atmosphere. So this Earth energy imbalance, so which should be in phase at timescales of 1 year and longer with the storage of heat, or the evolution of the rate of change in ocean heat storage, is a portion of the forcing that the Earth has not yet been responded to, and provides you an information, how stated in several papers, particularly, for example, in Hansen 2011, how much heat is still in the pipeline. So the Earth's energy imbalance is the most critical number defining the prospects for continued global warming and climate change. And so the simple number, the Earth's energy imbalance, is the most fundamental metric that the scientific community, but also the public, must be aware of as a measure of how well the world is doing in the task of bringing climate change under control. So why should we care? Why should we care about this number? Why should we care about this estimate of global ocean heat content, which provides you an estimate of the imbalance of the Earth's energy imbalance? So the accumulation of this thermal energy from a positive Earth energy imbalance in the Earth system is the root cause of various facets of Earth climate change. So this is just one of the representations, providing insight on effects on, of course, warming the oceans, but also warming of land ice, leading to an increase in ocean mass. I've also decrease in sea ice, decrease in global mean sea level from land ice melt and ocean warming, and also effects on the coast, like coastal flooding, erosion, the increase of global surface temperature, atmospheric temperature increase, etc. So to make it in a summary, so why should we care is that the various aspects for the warming of the land, of the ocean, and the cryosphere and the atmosphere from a positive Earth energy imbalance can be felt in different aspects of climate change. It has been assessed, for example, in the different special reports. So why and how do we know that the ocean is warming? So what we need to know is information of subsurface temperatures, distribution, and the average value. So there are 3 specific methods how you can derive the ocean heat content. So you can derive this from direct estimates from a sea-to observing system, from indirect estimates, which is provided from remote sensing through the so-called sea level budget approach, where you can use the information from, for example, the total sea level from altimetry, information on ocean mass from gravimetry measurements, which provides you an independent information on the direct estimates and hence in terms to ocean warming, and the ocean reanalysis. So I will provide a short insight into the first 2, but then focus on the ocean reanalysis aspect to meet the major target of this webinar. So we have the baseline for the global ocean in situ observing system, which have undergone a longer-term evolution. And starting here with some aspects starting in the middle of the century, from 1950s up to the 1960s, 85, where you can see the distribution of direct subsurface in situ observation, mainly derived from so-called bathymetric measurements, which have been deployed directly from a ship, or CTD measurements from the ocean. But then in the year 2000, there was an evolution in terms of subsurface temperature measurements from the International Argo Observing System, with the deployment of, now we reach about 3,900 floats, measuring the ocean from the surface down to 2,000 meter depths, with a target area of 60 degrees north to 60 degrees south, and now with new technology developments at even deeper levels and also in polar areas. So these are the results for these estimates. You can see that there is an observing system which changed over time. And this is also reflected here. On the left-hand side, you can see a synthesized overview on the data statistics, providing insight on the observing system evolution, which is also critical for the challenges reanalysis systems are faced to. And so you have an insight for the Northern Hemisphere and also for the Southern Hemisphere. You can clearly see the development of the technical evolution of the observing system, reaching now down to 2,000 meter depths for large areas of the scale, and also providing, particularly before Argo, a hemispheric asymmetry aspect in terms of the coverage. And these are the estimates. On the right-hand side, you can see the results. So this is a synthesis or assessment of different results as obtained by different international working groups, as published in the large IPCC report in Chapter 2, providing you estimates back earlier than 1900, and then going up to the current Argo period with a focus on the Argo period. And we can see that the more you move forward in time, you move a more an agreement between the time series. But still, if you put in the focus that there's also differences in terms of this observing system. And there are many recommendations for sustaining this observing system, for reducing the uncertainties, but also to provide insight in the polar areas and in the deep ocean layers. This is another example of such an assessment. So this is a new assessment based on 15 different international in situ based products, with the objective to obtain an ensemble mean and spread of global mean ocean heat content to estimate ocean warming. This is a work as part of an assessment for providing a new estimate of the Earth's heat inventory as part of GCOS. And on the left-hand side, you can see an overview on the different decadal scale trend estimates, which have been derived here at different depth layers, so which are in the different colors from 300 meters, 700 meters, about 2,000 meter depths, and for the intermediate layer depths from 700 to 2,000 meter depths. And in addition, you have a repetition of different time periods in these different depth layers, which provides you insight in the evolution of time of the rate of change of ocean heat content. And what you can clearly see that with the time growing, with the depth growing, that there is an increased sequestration of heat into the deeper layer of the ocean, and particularly over time, which is really strongly shown here, for example, in the redistribution of the 700 to 2,000 meter depths. Particularly, there is also high agreement between the different products, albeit they are faced with challenges from the observing system evolution. On the right bottom side, you can see the results. So this is an ensemble mean of all the products as shown on the left-hand side, and provide a time series starting in the 1960s up to 2018, for this paper, and which is then an information which has been gone into the new estimate of the Earth's heat inventory. So this is an example on recent estimates of a so-called indirect method for ocean heat content. On the left-hand side, you can see estimates which are providing you again an overview on how this method works. You have information for global mean sea level, which provides you a full depth view on the sea level, total sea level components. In green, there's the ocean mass from GRACE measurements, providing you components for the ocean mass changes. And then hydrography, which provides you a comparison in terms of the information from the in situ observing system. And in green, you have the comparison to the net flux at the top of the atmosphere, as I said at the very beginning, because those two should vary in phase at timescales longer than 1 year. On the right-hand side, you can see that there is also another group who has provided another development in a similar sense, using the indirect approach for ocean heat content. And here you can see the time series on the global mean ocean heat content on full depth view, and also providing you some information at depths. But you can also see the gray bars here in this time series shows you when there had been some measurements problems, in particular with the GRACE instrument. So I will not further detail, I just wanted to show and come now to the ocean reanalysis. So I will start with an intercomparison with outcomes from an international intercomparison project, I guess you're all aware of, so AURA-IP. And this shows an ensemble, I think it had been an ensemble of 16 different global ocean reanalysis, which had been assessed for different climate parameters. So here it is for ocean heat content, but there had been also a focus on transport and also thermospheric sea level, for example, which I provide here as well. So the global ocean heat content is well constrained in the upper layer for the comparison of those reanalyses which have been chosen here. But they show large disagreements and spreads at deeper levels, and there is still large uncertainties remain for the interannual trends. Now this is an intercomparison project which had been stopped for the moment and providing assessments up to the year 2009. And on the right-hand side, you can see results from this intercomparison project for the thermospheric sea level, so directly linearly linked to the ocean warming signature of the same period and in the same project, provided you a similar result. Then this had been a paper in 2013 and a follow-up in 2016 from a group of climate scientists evaluating the ocean heat content rate of change in one specific ocean reanalysis, RAS4, which has provided a clear constraint on the climate signals on full depth ocean heat content. It provides an overview on the vertical distribution and the ocean heat content variations, such as, for example, volcanic eruptions, which are clearly resolved in this specific estimate. On the right-hand side, you can see also this estimate, which had been compared on the one hand to the net flux at the top of the atmosphere. If you go on this figure at the lower right corner, which is shown in the black line, and the blue line, you can see the comparison of this specific ocean reanalysis results, and which shows a clear constraint of this physical budget constrained approach. Then this is a result on the ocean warming estimates from ECHO, the estimated circulation and climate of the ocean. So this is a result here providing information on the vertical distribution and the change over time of subsurface temperature profiles, compared here to hydrographic estimates like the World Ocean Atmos or the ICI data, compared to other reanalysis systems, and also in black here the ecosystem. In addition, there had been a change over time for different periods, a choice which has been taken in terms of the discussion on the recent hiatus period, and providing here pre-hiatus, in hiatus, and the difference between the two periods in order to understand on how well this staircase warming or decadal natural variability had been resolved in those different results. And on the top level, you can see here the yellow part, which provides you insight on the surface information. And so result is here that this version of ECHO shows a credible fit to the hydrography trends over much of the depth range in the upper 1,500 meter depths, and produces also the apparent hiatus or staircase warming. We can discuss on the naming of this event compared to and up to the hydrography-based results like the World Ocean Atlas or the EC data, and also the satellite-derived sea surface temperature data. Here's another example. Oh, sorry, I'm going too fast. So this is example on the publication of a framework from the Copernicus Marine Service. So it's a so-called ocean monitoring indicators, which provide a regular distribution of ensemble approach of global reanalysis. We have used 3 different global reanalysis here for the global ocean heat content, which is shown here on the left-hand side, and it's shown in light green color, and compared to a direct estimate based on Argo-only estimates, and those results show clear agreement. In addition, we are also about to update the Earth heat inventory paper. We will want to update up to the year 2020. And these are the first preliminary results for this assessment. We have increased the inclusion of different data, and we have also added here the results of the reanalysis trends, which show to be well positioned for the Argo period in the spread, overall spread of the different observation-based results. And also here we have a continuation increase of the vertical heat redistribution in the deeper layers, and the record values, continued record values of ocean warming over the past recent decade. This is an example on the reconstruction of ocean temperature change with global full depth ocean coverage. So it's based on the use of the green functions, and those have been derived from the Goddard ocean state estimate. And the method here is to connect surface property from directly measured SST with those in the ocean interior through the use of these green functions. And this method is a very nice method because it provides various type of information, starting from an information on the full depth of the ocean change. And it also provides an information further back in time, because the time series starts before 1888. And in addition, it provides you also information on the different contributions from the basins, and also on the attribution of the signatures of some changes in the ocean heat rate of change. So for example, one of the results is that since the 15th, up to 1/2 of excess heat in the Atlantic Ocean at mid-latitudes has become from other regions via circulation-related changes in the heat transport. So then is an example on the value of ocean reanalysis for ocean observing system recommendations. So I have picked here 2 examples, so there are many more. So this is a specific example for also the question on ocean heat content and how does the global deep Argo array would impact the ocean reanalysis. As a matter of time, I will go directly to the results, which based on the observing system simulation experiments, they show that the global deep Argo array of 1,200 floats will significantly constrain the deep ocean by reducing temperature and salinity errors by around 50%. And the next example I wanted to highlight on the observing system recommendation is the use of an uncertainty framework within the ECHO framework, aiming to provide a design strategy for an effective ocean climate observing system, with a specific case study for the North Atlantic regional heat content and also the transport aspects. You can see here an example of which had been the tracer positions, and so the different framework and the sensitivity tests. And also here I will go straight forward to the results that sea surface temperature observations inform mainly local air sea fluxes, and another result from this study obtained that subsurface temperature observations reduce uncertainties over basin-wide scale, and so informing in turn heat redistribution at greater distances. So this also shows the strength and the power of the ocean reanalysis to further unravel uncertainties we did not know before. And this is another example on constraining the ocean heat content through assimilation of series-derived Tora energy imbalanced estimates. And also here, the methodology proves able to shape the ocean heat content trends and without compromising the reanalysis accuracy, and also really help to reduce some biases and some spurious signature, particularly at interannual timescales for this new approach. And this had been another sensitivity test I speed a bit up, which was testing the different sources of uncertainties and providing here clear insight that particularly the choice and the quality control of in-situ data uncertainty is crucial in order to provide reduced perturbations across the reanalysis systems, and coming up here with a number of 60%. So I will just give some takeaways here. The global scale estimate of heat in the ocean provides a crucial measure of the rate of climate change and defines the prospects for continued global warming. And the accumulation of thermal energy in the Earth system is the root cause of the various facets of observed climate change. So with some of those examples, but there are many more to be captured, is that there's an urgent need to further unravel the processes of heat sequestration in the ocean and to reduce the uncertainties in our estimates and to assess its regional implications. And so the recommendation here is concerted international efforts, including the use of ocean reanalysis, are promising tool facing these challenges and to foster advancements in climate science, such as, for example, heat budget closure at regional scale and guiding observing system developments. So I have listed some which you maybe use for coming in the workshop. I will go very quickly, and further developments is, of course, the Earth system view, additional data sources as presented in some examples, also high resolution developments and downscaling activities, particularly informing also sustainable adaptation and regional implications. And also barriers is the heterogeneity of the observing system and the boundary conditions. And the very final slide, including on the collaboration question, is to the continuation and refinement of the ORIP-like international initiative, including a common set of reference metrics, further strengthen the analysis of reanalysis data, in climate science. I think this is a very critical recommendation. And also to include the modeling assimilation value chain. And for the observing system, the maintenance and extension. I give you an example for heat content and the better use of existing observation with some examples on specific improvements for the assimilation of remote sensing data. Thank you very much. And please, happy for any questions.
Thank you, Karina, for this excellent talk. Really appreciate you putting the time and effort into presenting this. Do we have any question for Karina? You can pitch in, raise your hand, whatever. Yeah, Laura, go ahead.
Thanks for that talk. So you went through your last slides pretty quickly, which I understand. But you mentioned, oh no, it's fine. You mentioned boundary conditions of the atmosphere as being one of the barriers. And I was wondering if you had any thoughts on coupled models, coupled assimilation methods, and how that might factor in.
Yeah, I mean, these are the boundary conditions. So it's not really my in-depth expertise in terms of these aspects. But I think what is really critical is to achieve an Earth system view, because all those components are interlinked, and they're interlinked particularly through the exchanges of heat, the exchanges of carbon, to the exchanges of other traces in the Earth system. And I think if you want to further unravel and reduce uncertainties and understand the different changes in the shore, a comprehensive monitoring of the ocean, we need to move to this Earth system view. And I think the assimilation of data would be a way forward in order to provide this, particularly the flow of heat, right? The transport are the critical elements across the different Earth system components. But this is a very general view without the technical. Maybe your question was more technical, so I have to advise you to my collaborators here.
Thanks.
Any other question? I'm going to ask a question then if no one else has. And again, like Laura, the last few slides, I was really interested.
Yeah, sorry.
No, I get it. But I was interested into, you looked at the effect of deep Argo on that estimate of ocean heat content. And I was wondering if you did something similar, I guess, for the normal Argo array, but we know there is a bias, a temporal and spatial bias with the Argo floats. Have you looked into, I would think like an exercise where you remove a bunch of Argo and you look at the effect that would have on the ocean heat content estimate, and look a little bit at whether the spatial and temporal bias in the current Argo float, I'm talking just the surface, Argo float has on those ocean heat estimate?
Yes, there had been some specific studies, but with a major focus on particularly addressing the gaps, so the gaps in which are currently available. So, for example, the result is not only from reanalysis and observing system simulation experiments, but also from other analysis that, for example, the impact of not considering shallow areas and marginal seas can impact the trend estimate of 5 to 10%, so which I think is a huge impact. Then there had been another specific study, which was more as a science elevation and not really observing system simulation experiment, but it was a specific quantification using reanalysis results also, and also validate with observation comparison on the role of, for example, not considering the Arctic area, because today Argo is limited to 60 north, or the observation-based estimates are limited to 60 north and 60 south. And so the result there was for the Arctic area that it makes up 4% of the changes, including so long-term trends and variations, which is equivalent to the surface area of this area. So it was quite interesting and comprehensive result. Something which, to my knowledge, which had not been done so far is for the Arctic area. I think that would be a very critical information to really understand for global how we would reduce our uncertainties. So that's maybe the missing gap, in addition to the other gaps we have here with the deep Argo and the other areas.
So if you, it leads me to my sub question, which was if you had a wish list about something to add to an observation system right now, it would be Argo float in the high latitudes, or would it be a more consistent, better spatial resolution of Argo float, like Argo float every 50 kilometer constantly measuring? What would it be if you had like a top 2 pick of observational system, whether they're new or to add? What would it be?
So I will give you a twofold answer. So the first is in addition to the development already undergoing, so that implementation of deep Argo, which I think is very critical. I think filling those gaps, so if it would be an open bill, would be those gaps, I think, in the marginal areas. So would not only provide information only for heat content, but maybe also for other aspects where we want to close the gaps, like shelf transport components for observing system. And then I would like to provide, and of course the polar areas, but I would also like to mention what I would what would be also really critical are to assure some long-term transports, direct measurement of transports in order to validate results and to perform validation, to use also reanalysis systems and other data, combination of different data sets to provide also regional budget constraints in order to understand now, because we have a very important view now on the global scale change, but I think there is a need to move towards a regional scale information and the implications. And I think to move to these regions, we need to also understand the consistency on the regional budget closure, which I think, so it would be also transport for me.
Okay, thank you. I saw Mike come on camera. I don't know if that means that I have to move on to the next speaker, or if Patrick still has time to quickly ask his question. Can Patrick? Yep, go ahead, Patrick.
Oh, okay. Thanks. Great, very comprehensive talk, Karina. Thank you. You mentioned the number, if I remember correctly, 1.1 watts per meter square imbalance from the reanalysis product. How does that number come about? If you look at for example, the publication by Cronin et al. 2019 for Ocean Ops 19, you see the reanalysis, both the atmospheric net air sea fluxes as well as the ocean products all have very large unphysical imbalances, like up to sometimes plus minus 10 watts per meter square, which is due probably to the fact that reanalysis products are not conservative. They don't conserve properties. And so I was wondering where the number comes from and what can we do about that major, maybe, well, I would say maybe shortcoming, but maybe there's ways to get around that.
Yeah, so I just think I do not have a clear answer to say what would be the way to get around there. I think I have provided some of the examples which would be very interesting test forward, like for example the assimilation of series data, and in order to constrain or to put a kind of repeated reminder to come back to balance, right? So the number provided, as you have seen, was a number for the Argo period. So it's a number before, and it's a number for the upper 2000 meters. So it does not consider the bias in the deep ocean. So, I mean, it's a number of reflected and well assimilated data, I would think, to be a bit direct. But I completely agree with that there's a long way to go to really provide, let's say, a more independent number to also back in time, because we're still faced with these issues. And I think those very combined or completed methodologies, like for example in this study, I think that could be the way forward, and to combine with the information on the redistribution of heat. How does it redistribute to get, because we are stuck with the observing system to understand the processes and where and how the heat is redistributed. And I think combining this with Reanalysis will enlighten us much more, I think.
Thank you.
Thanks a lot, Karina, for this. I think it's time to move on to the next speaker. I'll let Sergi introduce her.
I'd like to introduce Dr. Clara Orbe. She's a research scientist at NASA Goddard Institute for Space Studies and an adjunct professor at the Department of Applied Physics and Mathematics at Columbia University. Before joining Goddard in 2018, she completed her postdoctoral program at NASA Goddard Space Flight Center and received her PhD in Applied Mathematics at Columbia University in 2013. Clara's interests are oriented towards an improved understanding of dynamical and transport in the atmosphere. While at GEES, she's focused on guiding development of the high vertical resolution version of the GEES climate model, Model E. Her research more broadly applies to a range of theoretical and numerical models, as well as observations to understand fundamental problems in atmospheric dynamics and transport. And with that, Clara, we're looking forward to your presentation.
Thank you very much for the opportunity to present today's series. As was mentioned, I'm a research physical scientist, primarily based at NASA GISS, but I've also done quite a bit of work and continue to collaborate with the Global Modeling Assimilation Office in Greenbelt at NASA. So just by way of motivation, the Stratosphere-Troposphere exchange of mass and tracers strongly influences both the chemical and the radiative processes of the troposphere and lower stratosphere. And stratosphere-troposphere dynamical coupling influences the onset of tropospheric weather regimes, while the exchange of constituents like ozone and water vapor affect the oxidizing capacity of the troposphere and air quality. And more recently, studies have really tried to link variability in the stratosphere to extremes at the Earth's surface. And so this is just a figure that was taken from a review study by Daniela de Mason and Amy Butler, showing some of these kinds of extremes, and specifically extremes in the sea ice extent, cold air outbreaks, and dry spells over much of Northern Europe. So I thought it would be good if I just gave a few overall impressions at the beginning of the talk. The first is that I think it's clear that more recent reanalyses do show key improvements relative to previous versions coming out from the same modeling groups with respect to the stratosphere. And so this is reflective of a combination of model changes and new observations, but there continue to be issues with discontinuities and transitions, especially in the middle and upper stratosphere. And so these pose challenges for inferring trends, not only in temperature, but also in constituents, as we'll see. There's been an increased emphasis on incorporating and assimilating composition, ozone, aerosols. And this, of course, is important for capturing the stratospheric compositional influence on the troposphere where it exists. But I would also argue that this is important for providing potentially new ways to constrain what is essentially a Lagrangian type of circulation in the stratosphere, which we refer to as the Brewer-Dobson circulation. And then finally, I think that there have been quite successful efforts like the Spark Reanalysis Intercomparison Project, which just published its report and provides a community resource for understanding differences among the current reanalysis products and potential underlying causes. And I think that a bit more coordination needs to be conducted in terms of coordinating simulations of the transport circulation along the lines of what was done for the free-running chemistry climate models within the Spark CCM-Val intercomparison, and more recently including some nudged simulations in CCMI phase 1. So I'll just very briefly talk about the kinds of observations that are assimilated for the stratosphere. So it's primarily radiosondes that provide high vertical resolution of temperature and zonal wind. And then humidity is provided, but up to only about kind of 200 to 300 hectopascals. And much of this radiosonde coverage is over northern hemisphere, middle and high latitudes. And so to provide more homogeneous horizontal spatial coverage, we utilize the satellite radiances, which include the TOV suite, which then transitioned to ATOVs in 1998. And so this is a figure here on the right-hand panel showing monthly global temperature anomalies as a function of pressure and time for the different reanalyses. And what you can see are these quite strong discontinuities. You can see it's particularly strong in this model, in this reanalysis product, especially because the underlying radiative transfer model that was used in this had a cold bias, which was exaggerated upon this transition moving to ATOVs in 1998. It was somewhat ameliorated through improvement of the underlying radiative transfer model, but you can still see that it's quite apparent. And so these discontinuities have been known for quite a bit as they imprint on temperature, and more recently it's been appreciated that they have signatures on things like ozone and other constituents. Okay. So in terms of what we need in these models to get some credible representation of the stratosphere, well, we need relatively high vertical resolution, especially within the UTLS upper troposphere, lower stratosphere region, as well as a high model top. There has to be some treatment of the top layers consisting of some combination of a mesospheric sponge layer, as well as frictional damping. Parameterized gravity waves are also important, and all reanalyses do include an orographic component. But only a subset include non-orographic gravity wave drag. And none of these models explicitly include convective sources. So potentially convective sources, as they're incorporated in the underlying models, may be needed to overcome some persistent biases in stratospheric dynamics, including biases in the tropical winds as they manifest in the quasi-biennial oscillation. So when we think about forecasting disruptions in the QBO, and its teleconnections to Earth's surface, potential improvements to the underlying non-orographic gravity wave drag component may be needed. And so just briefly, in terms of the treatment of the assimilated constituents, most of the latest generation models assimilate total column ozone, but there are various ways in which this is done, as well as the different ways in which the radiation actually sees this ozone. And so this is a figure which shows the differences in total column ozone between different reanalyses relative to one of the observational data sets. And you can see that they differ quite a bit among the reanalyses, and that some of these errors are quite exaggerated over the Antarctic, in the Antarctic polar region. And so perhaps improvements to the underlying chemistry ozone parameterizations, including the effects of heterogeneous chemistry, may be able to improve these biases somewhat, although it should be noted that more polar night observations are also needed in addition to those improvements to the model. And so then just briefly, aerosols, I'll just comment that there's a wide treatment of aerosols with some of these reanalyses specifying climatologies in contrast to some more active assimilation of aerosols. Okay, so it's quite daunting to give an overview in 20 minutes of all the aspects of stratosphere-troposphere coupling, so my apologies in advance if there are topics that I do not address here. But I thought it would be good at least to address the stratospheric sudden warming events, which include a rapid reversal of the primarily northern hemisphere polar westerlies to easterlies just within a few days. And so generally there's a good agreement among the reanalyses in terms of the mean frequency of stratospheric sudden warming. So generally the reanalyses are able to capture a frequency of about 5 to 6 events per decade. But there's a larger disagreement in terms of the seasonality of sudden warmings, both among the analyses, but also between the historical, what I refer to here as pre-1979 and satellite periods. And so in particular, you can see that there's, especially between MERA and the JRA products, there's quite good agreement in the seasonal distribution over the satellite era. But then as we move to the historical period, the seasonality does shift, but there's also more differences among these reanalyses. So whether or not there's actually any kind of physical reasoning for this shift in the seasonality, as opposed to, or in light of these differences among the reanalyses, is something that still is under debate. Okay, so these models do get these warming events, but we would also like to know that they are getting them for similar reasons. And so this is a figure showing the momentum forcing, so the different components of the momentum forcing evaluated at 2 different levels. Solid lines show 10 hectopascals, dashed lines are 3 hectopascals, and these are composited events by which in the x-axis 0 refers to the day, the definition of the sudden warming. And so you can see that there's actually quite good agreement among the reanalyses in terms of the momentum forcings of these warming events, such that you can see this period of strong deceleration of the zonal winds is accompanied both by changes in the Coriolis term, but also this enhanced convergence of the meridional fluxes of momentum prior to that deceleration. Okay, so the models seem to be capturing these events well, and it seems also like generally there's pretty good agreement in terms of why they're getting those events. But when we talk about stratosphere-troposphere coupling, one of the primary uncertainties really is the large dynamical variability. And so that's illustrated here in this figure, which shows a composite of sudden warming events for one reanalysis, and the different lines show different events. And if we then compare that to 2 different events, the different lines here are different reanalyses, and if furthermore we throw out the surface input reanalyses and we just focus on these analyses that are close together, we can see that the differences among the reanalyses are quite smaller than just the internal variability. And so with this kind of a problem, the dominant contributor to uncertainty, really it does appear to stem just from the nature of the physics itself. So you just have this widely divergent response, even within the stratosphere. And so how does this couple to the surface? Well, this uncertainty due to dynamical variability dominates not only the stratosphere, like we saw in the previous slide, but also its downward propagation. And typically we quantify this through the northern annular mode anomalies, in this case shown composited for weak vortex events, so this is pressure and time, and strong vortex events in the right. And so in this study, what they did is they further partitioned the uncertainty in this downward propagation of NAM anomalies into sampling uncertainty, and then uncertainty due to differences among reanalyses. And so it's quite clear here that that large contribution from the sampling uncertainty that we saw aloft is also dominating the uncertainty close to the surface. So at this point, I'm going to shift to talk about the Brewer-Dobson circulation. And so while the stratosphere can be linked in terms of, or can be viewed in terms of these distinct regions, so you have the tropics, the quasi-biennial oscillation, and then you have distinct variability over the polar, associated with the polar vortices. In the end of the day, the tropics and high latitudes are linked through a mean meridional transport of mass and tracers throughout the stratosphere that we refer to as the Brewer-Dobson circulation. So I would argue that constraining the BDC and reanalyses prevents, in that sense, a more fundamental but also more challenging goal. And this is because the BDC reflects not only a wave-driven advective circulation, which we like to to quantify in terms of the transformed Eulerian mean, which consists of an Eulerian component and this eddy-driven component. And then eddies also make their way into isentropic mixing. And so the BDC represents the aggregate effects of both this eddy-driven advective component of the circulation and mixing as realized, and eddies as realized through isentropic mixing. Okay, so let's look at how the tropical upwelling, so the vertical component of the transformed Eulerian mean, compares among the different reanalyses. And that's shown right here, plotted here as a function of time. And overall, if we mainly focus on the more recent reanalyses, which are highlighted in the more solid colored lines, and so the gray shading here shows the spread within the CCMI model. So these are free-running models. So we're putting the reanalysis spread in the context of comparable free-running models. What we can see is that overall there's pretty good agreement in terms of the climatological mean strength of upwelling among the reanalyses, especially the more recent reanalyses. However, if we focus on those same more recent reanalyses, and then we look, in this case, at the vertical structure of trends in upwelling, we begin to see quite large differences, with some of the reanalyses suggesting that over this time period, over the past approximately 3 decades, upwelling has increased, whereas these reanalyses, namely ERA interim and ERA 5, suggest a reduction in the strength of upwelling. So it's really not clear, given these differences, whether or not the BDC has actually accelerated or not. So you could say, okay, well, that's just an artifact of the particular metric that you're looking at. But indeed, if we look at kind of a more aggregate measure of the residual mean circulation, so in this case, these are residual circulation transit times, which you can think of as corresponding to the trajectories that parcels would take were they not also to be mixed at the same time. And this shows these pressure latitude changes in the residual circulation transit times for the different reanalyses over different time periods. And you can see that some of the reanalyses show these blue values, so this deceleration of this advective circulation. But you also see positive trends in the ERA products. So it's really not quite clear whether or not this circulation is speeding up or slowing down. Okay, so a key limitation in our understanding of the BDC is that we don't actually have direct observational estimates of the diabatic circulation. And so to this end, we often rely on tracers to provide indirect estimates, although we have to bear in mind the important caveat that these tracers also are going to be reflecting the integrated effects of mixing. So that said, one of the more kind of common metrics that we use is this age of error, which can be estimated from measurements of sulfur hexafluoride and carbon dioxide, and is shown here as a function of pressure and latitude from this review study by Darren Woff back in 2002. So this is a figure taken from Engel et al. In 2007, showing that we can use measurements of SF6 and CO2 to then construct estimates of the age of error. And if we do that, and we plot that as a function of time over northern hemisphere mid-latitude, so these are balloon-based measurements, we can see with, despite the large internal variability, we can see that there is this general kind of increase in the age of error over northern mid-latitudes. Okay, but you can say, well, that's one measurement. Is this substantiated by other measurements? And so this here is a figure taken from a study looking at trends, except now inferred from satellite measurements of SF6, in particular MIPAS. And indeed, if you do look over the northern hemisphere mid-latitudes, you do see these red contours. So red here is positive, so that would be consistent with this tendency for positive trends in the age of error inferred from the balloon measurements. However, what you can see is, in the same sense that you're seeing this increase over northern hemisphere mid-latitudes, you're also seeing this decrease over the southern hemisphere. So at the very least, the satellites, while yes, consistent with the balloon-based measurements, are also highlighting a really kind of rich spatial structure in the trends with latitude.
3 minutes left.
Thanks. Okay, so how do the reanalyses then compare? So, well, what we can do is we can take a CTM and then constrain that with different reanalysis fields, integrate the passive tracers, and if we do that, such as summarized in this study by Chavilat, and then overlaid against the observation. So this is the same figure that I showed before, except that the lines now show the different reanalyses, constrained simulations. What we find is that with the exception of era interim, most of the reanalyses are not producing this increase in the age over Northern Hemisphere mid-latitudes. However, there are two key issues that really surface in making statements about age of air trends derived from reanalyses. And I think one of the key ones is we really don't know what the true reanalysis mean age is. And I'll explain that on the next slide a little bit more. And the second question is, these age trends are incredibly sensitive to internal dynamical variability. And so we'll see that illustrated in 2 slides. And so in particular, to address the first point, since the reanalyses do not explicitly integrate these age of error passive tracers, one has to use offline models such as CTMs or nudging to infer the ages associated with the different reanalyses. And unfortunately, I think there's a growing consensus that the age of error calculations are very sensitive to the methodology used. And so this is a figure showing here this pressure distribution of the root mean square error between 2 ensembles of the same size, one employing free running simulations shown in the cyan, and one employing specified dynamics, so through nudging or CTMs shown in the magenta. And indeed, you can see that there's actually larger differences among the specified dynamics simulated ages relative to the free running models. And so you can say, well, that's a reflection of the differences among the reanalyses. Well, not so much. Indeed, we can take one model, GEOS in this case, and then constrain it with MERA. And so in this case, MERA provided both the simulated and analysis fields. And we can see that there's actually quite large sensitivity to which fields are being used. And so you can recover quite a large spread just using a single model. So in the same sense that we don't know exactly what the true reanalysis ages are, the integrity of any reported age of error trends really may be called into question simply by considering the large variability over different time periods. And you can see this comparing the age trends over these 3 different time periods for era interim and then MERA 2. And it's just quite obvious that there's a large variability depending on which years you include. And then finally, some of that variability can be contributed through internal variability. And there's some interesting work that Jessica New has been doing looking at the way the QBO may influence variability in upwelling and associated age changes. But we cannot also ignore the potentially disruptive influence of the transition to AMSU in 1998 and how that imprints on these constituent trends. So with that, I'd like to come to my concluding remarks. Overall, I think the recent reanalyses do provide excellent tools for understanding stratospheric transport and dynamics, but there are key uncertainties that persist. In particular, there are certain biases in stratospheric dynamics that we're still struggling to understand in more recent reanalysis products related to the quasi-biennial oscillation in the tropics, as well as the southern hemisphere polar vortex. I was not able to talk much about that. When we look at trends in the Buridops in circulation, the reanalyses are in the climatological mean values are quite consistent, but their trends differ. And these trends are also quite sensitive to the time periods that are considered. And then finally, tracer-based diagnostics of the BDC do open up new possibilities for constraining reanalyses, but with that, we introduce complications afforded from mixing. And also, we don't really know what the true mean age is because of our dependence on using these offline approaches, which are quite sensitive to methodology. And so in terms of proposed paths forward, I think it'd be important to continue looking at how the incorporation of more interactive non-orographic gravity wave drag may help ameliorate some of these long-standing biases, especially in the tropical winds. We need to identify the true reanalysis transport characteristics through explicit integration of age of error and passive tracers within the DAS. And then we better need to understand the influence of both dynamical variability and observational discontinuities in terms of trends, not only in temperatures, but in the constituents. And so with that, I'll just come to the last slide, which was, not sure what. it's not advancing. But the last slide was just the questions, Jenny, that you had provided. So yeah, I'm not sure why my slide is not advancing. But...
It did advance for me.
Oh, so, okay.
I don't know for everyone else, but
we can include the slides on the website for after.
Okay. Well, thanks a lot, Clara. That gave us a great overview and I think a lot of food for thought for the workshop. I think it really unravels the complexity of each of the components that we're dealing with. We have a few minutes for questions, so I want to make sure that everyone gets a chance to ask questions to Clara. Who wants to start?
I have a question, if no one else does.
Yes, please go ahead.
Thanks for the really nice talk. I was wondering about, you mentioned how some of the underlying models don't have non-orographic sources and some do. And I was wondering for the QBO, are the observations enough to constrain it in either way, either case? And then if so, do you see a role for analysis increments in trying to constrain those non-orographic sources?
Yeah, I mean, I think the observations, I mean, with the QBO, it also kind of depends ultimately on what you want to constrain. So I think the observations that we do have are quite zonally limited. So when it comes to zonal characteristics, that may be important in terms of the associated meridional circulation. So how the QBO then interacts with the extratropics. So as we start thinking about the tropics to high latitude, potential teleconnections where those things may be important, I'm not convinced that the observations at this point are sufficient with the sense of just simply relaxing back to the observational winds, for example. You know, I think there what's needed is in combination with the assimilated observations, we need kind of a better understanding of the actual waves that are involved in communicating information from the tropics to high latitudes. I do think, you know, the observations do go a long way in that region. But, you know, speaking from personal experience with at least the GISS model, there really is a large contribution from, you know, these non-orographic waves, especially with respect to the descent of the QBO to those lower UTLS regions. So how much the observations can help in that UTLS and that lower stratosphere region, which seems important, at least from a teleconnection point of view, is something that you know, I think we would need that additional help from these non-orographic waves. Now, you know, what are these non-orographic waves? They're parameterized, and that's where other observations, which may not be directly assimilated, but could at the very least be used to constrain the associated momentum fluxes, would be useful. And so, you know, Joan Alexander and others have done nice work looking at those momentum fluxes, the spectra of those momentum fluxes. And, you know, if we can develop ways to challenge our models by evaluating the QBO, not just in terms of the wind and temperature signatures, but also by constraining the momentum fluxes themselves, then that's kind of an indirect way of improving the models. So I hope I addressed your question.
Yeah, very much so. Thanks.
Thank you. Roberto?
Yes, a couple of comments. The first one is on the use of the ensemble of reanalysis that ERA 5 includes. So I haven't heard anyone talking about this. And I guess it's still the only reanalysis that includes an ensemble that can be used to estimate the uncertainty linked to model error and observational uncertainty. So I think I would try to do a little bit more studies using the whole ensemble of the ERA 5 members to see, you know, to try to get an estimate of the uncertainty around the mean states that are usually shown. And yeah, so this is essentially my comment. I would encourage that we look at that. The second point is about adequacy. So maybe the analysis that we are producing now are adequate only for certain estimates. Maybe they're not yet good enough, for example, to estimate the age of air or to estimate certain trends. And one of the points that could be interesting to discuss during the workshop is precisely that. So how fit are the reanalysis we are producing now to do the studies we want to do? What's missing? What do we need to do to make sure that we can use them also to do other type of studies? Thank you.
Thank you for those comments. I agree. Yeah, identifying the problems to which, especially when it comes to transport, these reanalyses are suited. I think that's definitely an important point.
Okay. We are at the top of the hour. I think this led up very well to the discussion that we hope to dwell more into during the workshop. I want to make sure that Soji, Mike, or Jenny, if you have any closing comment, but I want to thank you, Clara and Karina, for the great talk and for participating in this. And I think, you know, it's very exciting to see the build up to the workshop with all those talks that we have. And I foresee a lot of discussion during the workshop. Mike, Jenny, Soji.
I just want to echo Cecile. Thank you everyone for participating. Thank you for the speakers for giving us the presentation today. For the workshop, anyone who's still interested in submitting an abstract for a poster presentation, I anticipate that we'll be extending that deadline. So if you're still interested, please go ahead and submit one through the website. The next webinar will be on March 8th, and that one has a time change. That one is 4 p.m. Eastern Time instead of 11 a.m. Eastern Time, and it'll feature Arlindo da Silva and Lyndon Ashcroft. So I will send out an email announcement when we get closer to that date with the time 4 p.m. as a reminder. Mike, did you have any final words?
Yes, I wanted to say thank you both for such thorough presentations. And in addition to linking to this workshop, and I think really helping motivate some of our discussions there, and I hope you'll be participating in the workshop itself to bring us back to some of these topics that you've illuminated, that within the U.S. CLIVAR program and CLIVAR internationally as well, these topics are important there too. And so in terms of ocean heat content and particularly the feeding into the deep ocean, our pause panel has a focus on that, Karina, and that I'll probably be following up with you directly on. And Clara, we have at our upcoming summit next month a session focused on Stratosphere-Tropospheric interactions and the challenges that we have in both observing and modeling those. And so I think this talk will help inform that effort as well. So I'll be following up with you for regarding our summit. So thank you both for really informing us well for the reanalysis workshop.